All right, it's time for part 2 of our AP Chem 2025 FRQ. So looking at the second problem, it's giving us a scenario that's involving ascorbic acid, which is vitamin C. For part A, a student combusts a sample of ascorbic acid to determine its chemical composition. The only products of this reaction are 0.2400 moles of CO2 and 2.883 grams of H2O. For I here, we're going to calculate the number of moles of H2O that are produced. So all we had to do for I is going to be take the mass value of water that was produced. We divide it by its molar mass. So that grams cancel and we're left with just moles. That is then going to give us a mole value of 0.1600 for the H2O. For double I, it tells us the mole ratio between carbon and oxygen is 1:1 in ascorbic acid. Based on this information and your answer from part A, section I, determine the empirical formula of ascorbic acid. So the information that we're going to need is the value that we just calculated because they told us, right? We have to use it. And then also this mole value of the CO2 that's given. So it tells us that this is a combustion reaction. We're going to have ascorbic acid reacting with oxygen gas to make CO2 and H2O. So we have some hydrocarbon with oxygen that is going to make up ascorbic acid. It's going to react with some amount of O2, and then we know it's going to form CO2 and then H2O. So we are able to look at the ratio here between our H2O and then the CO2. So if we look at these numbers and we compare them, we're going to end up with a 3:2 ratio. So for every 3 moles of CO2, we're going to get 2 moles of H2O. So we know that the mole ratio within ascorbic acid between carbon and oxygen is going to be 1:1. So we are getting a minimum of 3 carbons that are here. And it's asking us for our empirical formula. So that's what we're going to work with. So for the carbon part, we're going to get 3. We know it's a 1:1 ratio between carbon and oxygen. And then so oxygen also has to be 3. So then now we just have to find out, well, what's that missing hydrogen amount? So we can use our water here because water is the only form of hydrogen as a product. And then so we get 4 atoms. And then so our empirical formula for the ascorbic acid is going to be C3H4O3. For part B is now looking at a titration of the ascorbic acid with sodium hydroxide. So for this scenario, they say that our ascorbic acid is going to be in a 10.0 milliliter sample, and it's going to be titrated with a sodium hydroxide solution that has a concentration of 0.0550 molar. So for part BI, it's asking us to calculate the molar concentration of our ascorbic acid. And then so we have to find out, well, how many moles of sodium hydroxide did it take to completely react with the ascorbic acid? So using our titration curve, we're able to identify our equivalence point here. And then so that is our volume of sodium hydroxide that was needed to completely react with the ascorbic acid. So they give us the molarity of the sodium hydroxide. And then so we plug this into our molarity expression to solve for moles of the sodium hydroxide. And then we're going to convert our volume into liters. And then so we're going to get a mole amount of NaOH being equal to 8.8 times 10 to the negative 4. Right, now it's going to be a 1:1 ratio between the sodium hydroxide and our ascorbic acid because our equation here shows us that we only have 1 proton that's breaking off from the ascorbic acid. And then so this mole amount is equal to the moles of ascorbic acid. And then so in order to find the molarity of the ascorbic acid, we now take our mole amount, which is going to be the same value, and then divide it by the volume that we use. So we were told that we had a 10 milliliter sample, and then so that is then going to be our denominator here. And then so the molarity of the original ascorbic acid is then going to be 8.8 times 10 to the negative 2 molar. For double I here, it's saying from the titration curve, determine the approximate pKa value of the ascorbic acid. Now we can use the Henderson-Hasselbalch expression where pH will be equal to the pKa if we have the same concentration of the conjugate base and the original acid. So we want to look at what point on our titration curve do we have this relationship where the log will cancel out, so we just have pH is equal to pKa. So that is going to be at our half equivalence point. So at our half equivalence point, and before I do the circle here, if we zoom in, it's just barely above 4. So then I would approximate, so because pH is equal to around like 4.1 at that volume, that pKa is going to be equal to 4.1, which is the pH here. All right, so that's our relationship that gives us our answer for double I here. For this last part here, it's asking what is the value of the ratio of the conjugate base and the ascorbic acid when the pH of the solution is 4.7. So we're able to use the Henderson-Hasselbalch equation again, where we can just plug in some values now. So we know what the pH is. They tell us specifically at 4.7. We calculated the pKa, or at least found it from the graph from the previous problem. So that's going to be 4.1. And then if we take the log of our ratio, we are then able to get our relationship here. So it's asking us for the value of the ratio, not for the value of this whole thing here. So then if we rearrange this and we solve for that value, that is going to be equal to 0.6, right? But then we have to undo the log. So then 10 to the power of 0.6 is going to give us our answer. And our answer is going to be 3.98. So then that is the ratio value at a pH of 4.7 from this titration. When we're looking at scenario C, we have a different acid. We have the dihydroascorbic acid, and it's being produced by reacting ascorbic acid with triiodide ion, which is the I3 negative. So we have the reaction here for the scenario that they just described, and then they give us this data table here. So for part I, for C, it says the rate law for the reaction is rate is equal to K times the concentration of our acid times the concentration of the anion. Explain how the data in the table support the conclusion that the reaction is first order with respect to our ascorbic acid. So we want to see, well, how does the change in concentration of the ascorbic acid impact the change in the rate? So then we want to pick the trials where we are keeping our other reactant constant, so that's not going to impact the change in the rate. So then if we look at trial 1 and trial 3, the concentration increased by a factor of 2. And then if we look at our initial rates here for trial 1 and trial 3, also increased by a factor of 2. So in order to prove this, we can say, well, in order for our rate to be doubled from a doubling of the concentration, that means that our exponent here has to be 1. And then so that is going to tell us that this is a first order reaction. So as our concentration doubled, our rate doubled. For C double I, it asks us to calculate the value of K for the reaction and to include units with the answer. So when we think about this, we can just rearrange our rate law that's given to solve for K. So then K is then equal to our rate. So we can pick any of the trials here. I'm just going to pick trial 1. And then so we get m squared in the denominator, and then we have m divided by s in the numerator. So in terms of our units, it's going to come out to be molarity times seconds, both to the negative first power. And then for the actual value, we end up getting 4.55 times 10 to the negative fourth power. And so that's our answer there. For the last part, for D, it's telling us that the triiodide ion is significantly more soluble in water than the elemental iodine, which is just I2. Identify an intermolecular force between triiodide ion and water that is not present between iodine and water. And then we're looking for an explanation that can describe or prove the difference in solubility. And then they give us the Lewis structures of each substance below. So I3 has a complete formal charge of -1. So it's basically, it is an ion. Compared to I2, which is neutrally charged overall, so it's going to be nonpolar. And then so between the I3 and water, it's going to be able to experience ion dipole. And we know ion dipole is a stronger interaction compared to something like London dispersion, which they both experience. And so we can see that I3 has just more intermolecular forces, so it's going to have a better ability at being soluble in a polar solution. And then it's because of this ion dipole interaction that I3 has that is going to allow it to be more soluble in water compared to just LDF, which I2 only has.